One of the reasons we study sequences and their convergence is in order to understand the behavior of infinite series. Infinite series can be used to compute lots of interesting uh, quantities. For example, Bhaskaracharya's, not Bhaskaracharya, what the heck, okay, let's start again. One of the reasons we study sequences and their limits is in order to be able to understand infinite series. Infinite series are like sums, except that instead of adding a finite number of numbers, you're adding infinitely many of them. So we have to make sense of these infinite sums. And for example, Aryabhatta's approximation of pi, which we discussed the other day, was obtained by using an infinite series that converges to pi. We have our own favorite infinite series, which came from my marathon misadventure. We had the sequence S1 is half, S2 is half plus 1/4, S3 is half plus 1/4 plus 1/8, and so on. And what we saw is that this limit as n tends to infinity of Sn, well, this Sn actually is just 1 minus 1 over 2 to the power n. This is what we were able to compute earlier, and what you see is that the limit as n tends to infinity of Sn is equal to 1. So here we have stated this as the limit of a sequence, but we can also rephrase it in terms of an infinite sum. So another viewpoint is that summation n goes from 1 to infinity 1 over 2 to the power n is equal to 1. So what we have here on the left is an infinite sum. See, we know how to add two real numbers, and then using associativity we can add 3 real numbers, 4 real numbers, and so on. But what does it mean to add an infinite set of real numbers? So it doesn't always make sense. For example, if I took something like summation n goes from 1 to infinity of 1, well, you could say it's infinity, but it's not a real number, and so this doesn't quite make sense. Or worse still, I could say something like, you know, n goes from 1 to infinity minus 1 to the power n times n. So this is something like minus 1 plus 2 minus 3 plus 4 and so on. You start computing these sums and you're not going to get anywhere. You cannot make sense of such a sum, but sometimes you can, and these will be called convergent series. So let's go straight down to the definition. So given a sequence an of real numbers, we say that the series, the infinite series, which is denoted like this, the Greek letter sigma, n goes from 1 to infinity, an is equal to S if the sequence of partial sums What is the sequence of partial sums? Well, remember here we started with the sequence of partial sums, but the terms of the series. So S3 is the sum of the first 3 terms of the series. So in general, the sequence of partial sums Sn is going to be A1 plus up to an, the sum of the first n terms of the series. So I could write it as I goes from 1 to n, an has limit n tends to infinity Sn equal to S. So this is how we make sense of infinite sums. And so what we are saying here really exactly as per the definition we have made, summation n goes from 1 to infinity of 1 over 2 to the power n is equal to 1. Let's look at another sequence. So let us look at an equals 1 over n. So we have this sequence, Sn is going to be 1 plus half plus 1/3 plus 1 over n. And what we are asking about is this sum, n goes from 1 to infinity, an is what? Now, it is true that the terms of the sequence get smaller and smaller as we go along. And so it seems plausible that this sequence will converge. Let me give you a small result now, which is a theorem rather easy to prove, that if summation n goes from 1 to infinity equal to s, that means that the sequence of partial sums converges to s, then limit as n tends to infinity of an, the terms themselves must go to 0. Well, the proof is very simple, though has a slightly clever idea in it. So, we have this limit n tends to infinity of Sn plus 1. Well, we have already seen that this is going to be the same as the limit n tends to infinity Sn, right, and both of these are going to be equal to s. Let us take the difference. So, what we have is 0 is equal to limit n tends to infinity Sn plus 1 minus Sn by the sum property of limits. But what is Sn plus 1 minus Sn? Well, Sn plus 1 is the term of the sum of the first n plus 1 terms of the sequence. Sn is just the sum of the first n terms of the sequence. So, this is limit as n tends to infinity just an plus 1. And so, what we have is that the limit as n tends to infinity of an plus 1 is 0. Well, that is really the same as saying that limit n tends to infinity an is 0. We say that an infinite series converges if there exists a real number s such that summation n goes from 1 to infinity is equal to s. And what we have shown here is that if an infinite series converges, then its terms, the terms of that infinite series go to 0 as n goes to infinity. So, now here we have an infinite series, summation n goes from 1 to infinity 1 over n. The terms of this series converge to 0, limit as n goes to infinity 1 over n is 0. But the question is, does this infinite series converge? Now, I sat down with my computer and I computed a few values for this infinite series. So, I found that S10 is about, well, not exactly, it is about 2.93, S100, well, that is about 5.19, S1000 is about 7.49, S10,000 is 12.09, S1 lakh was the last I could do easily, is about 14.39. So, what you are seeing is that as I add zeros, right, to this 1 that I have, every time I multiply by 10, there seems to be a kind of steady increase in Sn. Well, this seems to indicate that this series should not actually converge. It probably increases and the sequence of partial sums is unbounded above. So, what I am going to show is that the set Sn is unbounded and so the series does not converge. The idea is quite simple, and there is this one idea that I am using here, which is that if I look at, if I start somewhere in this series, so I start say at 1 over n plus 1 plus 1 over n plus 2. So, wherever I start in this series, if I take enough terms, so I go up to 1 over 2n, then this is going to be, so 1 over n plus 1 is greater than 1 over 2n. 1 over n plus 2 is also greater than 2n, well, provided n is greater than 2, and so this is. but that is just equal to 1 by 2. So, if I take terms of the series starting from n plus 1 up to 2n, that is going to be greater than half. We will show by induction that for every natural number m, there exists nm, a natural number nm, such that S nm is greater than m. Well, I'll put m by 2 here because this block of terms is giving me half. So, I just need to take m such blocks. So, let's do this by induction. So, the base case m equal to 1. So, I need to, well, I already have, we can take nm equals 1, S1, well, that is just the first partial sum, that is 1, which is greater than 1 by 2. So, we are done. Now, suppose we have found Snm which is greater than m by 2. I need to find nm plus 1. So, what we have is, we have S2nm is equal to Snm plus 1 over nm plus 1 plus 1 over nm plus 2 all the way up to 1 plus 1 over 2 nm, and that is equal to Snm plus half. Well, Snm itself is greater than m by 2, so this is greater than m plus 1 by 2. So, the partial sums of the series are unbounded. In this case, we say that the series diverges to infinity. Let us change the series that we were looking at slightly. What about the series, the infinite sum 1 minus half plus 1/3 minus 1/4 plus, right, which I can write in sigma notation as summation n goes from 1 to infinity minus 1 to the power n minus 1 over n. Well, again, I did some experiments with my computer. I found S1 is equal to 1, S10 is 0.646, S100 is 0.688, S1000 is 0.693. Well, these are approximate, right? And so, unlike the previous series, these are not growing steadily. In fact, they seem to be settling down somewhere around this 0.693. In fact, if you look at the first few terms, if I start with S1, S2, S3, the first term, well, it is just 1. The next term is 1 minus half, so that is 0.5. The next term is 0.83. I am writing them in this staggered manner for reasons that will become clear later. 0.8, well, not exactly, approximately 0.83. The next term is 0.58. The next term is 0.78 approximately. The next term is 0.62. Then it is 0.76 and so on. In fact, we can try to plot these on a graph, and what you see is that these values of these partial sums, well, they keep going down and up and down and up. That is not really surprising because alternate terms of the sequence are positive and negative. So, S2 will go down from S1 because the second term is negative, S4 will go down from S3 because the fourth term is negative and so on, and similarly each odd term will be little larger than the preceding even term. But there is something else that is very interesting happening. If you look at the relationships between the odd terms alone, So, the first term, third term, fifth term and seventh term, you will see that they are decreasing. And if you look at the relationship between the even terms alone, you will see that they are increasing. So, this is greater than this, greater than this, greater than this. This is less, less, less and so on. And this is the key to understanding the convergence of this series. What we observed for the series 1 minus half plus 1/3 minus 1/4 is in fact part of a general pattern, and I will write this pattern down as a theorem. Suppose we have a sequence A1 greater than or equal to A2 greater than or equal to is a sequence, a weakly decreasing sequence. Of real numbers, and limit as n tends to infinity a n is equal to 0. So, for example, keep in mind a n equals 1 by n. The claim is the series summation n goes from 1 to infinity minus 1 raised to n minus 1 a n converges. Seems like a strikingly simple condition for convergence. The terms must alternate, the absolute values of the terms must be non-increasing, i.e. they must weakly decrease, and the terms must converge to 0. That of course is needed because we showed that if a series converges, then its terms must go to 0. And the proof? Well, it's the observation that we made earlier in the case of the series minus 1 to the n minus 1 divided by n. Let us just make that formal. So, we have S1 is equal to A1, S3, well that is A1 minus A2 plus A3, but I can write it as A1 minus A2 minus A3. Now, remember A2 is greater than or equal to A3. So, A2 minus A3 is non-negative, and so A1 minus A2 minus A3 is less than or equal to A1, which is the same as S1. S5 is equal to, let us see, S3. So, let me write this here as S1. This is S3 minus A4 minus A5. And this is in fact less than or equal to S3. So, this is the explanation for what we observed. In general, S2n plus 1 is equal to S2n minus 1 minus A2n minus A2n plus 1, which is less than or equal to S2n minus 1. So, this sequence of odd indexed partial sums is a weakly decreasing sequence. But also S2n plus 1 is equal to A1 minus A2 plus A3 minus A4 and so on. We can go up to A2n minus 1 plus A2n, minus A2n plus A2n plus 1. And this is certainly greater than or equal to A1 minus A2. So, this sequence of odd partial sums is a weakly decreasing sequence which has a lower bound, namely A1 minus A2. Similarly, you can show that the sequence of even partial sums S2 is going to be less than or equal to S4, which is going to be less than or equal to S6. This is going to be a sequence of increasing terms or weakly increasing terms that is bounded above. Let L be the limit as n tends to infinity of S 2n plus 1. Let M be the limit as n tends to infinity of S to n. Both these sequences have limits because they are monotone sequences that are bounded. Now, I claim that L minus m is 0. Well, L minus m is the limit as n tends to infinity of S2n plus 1 minus S2n, which is limit as n tends to infinity a to n, which is 0. So, L is equal to m. And so, what we have is that this is the common limit of both the sequences of the even partial sum sequences and the odd partial sum sequences, and we can conclude that this series converges to L. The most commonly used test to decide whether or not a series converges is what is called the comparison test. And once you know that one series converges, any series that can be compared with it can be shown to converge. So, what it says is that if an and bn are sequences such that an in absolute value is less than bn for all n, and the series n goes from 1 to infinity of bn converges. So, this is necessarily a series of positive terms. Then the series an also converges. It is this kind of statement where the notion of a Cauchy sequence really becomes useful, because we know that the sequence Bn converges, and we may even know its limit, but we have no idea what the limit of An is, because all we know about An is that in absolute value it is less than Bn. So, to be able to say that it has a limit, we will really need the notion of a Cauchy sequence. What we will show here is that the sequence of partial sums of An is a Cauchy sequence. So, let Sn be summation I goes from 1 to n of An. Let Tn be the sequence of partial sums of Bn. I goes from 1 to n Bn. Now, I want to show that this Sn is a Cauchy sequence, and what I know is that Tn is a Cauchy sequence because it is a convergent sequence. So, we will use that to show that Sn is a Cauchy sequence. So, let us look at the difference between two terms of Sn. So, Sm minus Sn, and for this we may assume that say m is greater than n, otherwise we just reverse the order in which we look at it. Well, what is this? This is nothing but am plus am minus 1 plus all the way up to an plus 1, right, the terms which are accounted for in Sn but not in Sn. And this, well, term wise am is less than or equal to bm, so this is less than or equal to bm plus bm minus 1 plus bn plus 1, but that is just Tm minus Tn, and this we know is the Cauchy sequence. So, for every epsilon greater than 0, there exists n in n such that for all mn greater than n, Tm minus Tn is less than epsilon, and this also implies that Sm minus Sn is less than epsilon, because after all it is less than Tm minus Tn, less than or equal to Tm minus Tn.